The morning of October 1st, 1940, dawned clear over Stratford, Connecticut. Inside Chance Vaught's engineering hangar, test pilot Lyman Bullard climbed into the cockpit of an aircraft unlike anything American aviation had produced. The XF-4U-1 prototype sat waiting, its distinctive bent wings catching the early light like a predatory bird folding its talons. Behind him, Chief Engineer Rex Beisel watched with the nervous intensity of a man who had staked his entire reputation on a single audacious idea. A meeting. That's all it had taken. 8 men crowded into an office 2 years earlier, sketching on desk pads, arguing over propeller clearance and landing gear length. And in that room, facing impossible requirements from the Navy, Beisel had asked a question that seemed almost too simple. What if they just bent the wing? Now, as Bullard advanced the throttle and the massive Pratt & Whitney R2800 roared to life, that question was about to receive its answer. The prototype accelerated down the runway, the 13-foot propeller clawing at the air, and lifted off. Within minutes, the airplane was screaming across Connecticut skies at speeds that shattered every assumption about what a carrier fighter could do. 404 miles per hour. Not in a dive. Not with tricks or special conditions. Level flight. The first American single-engine fighter to break 400. But this wasn't the story of a perfect machine born from a stroke of genius. This was the story of desperate men facing a ticking clock, a story of shortcuts taken and rules bent, of engineers who believed so deeply in their design that they would risk everything, including their careers, to prove it could work. Because in 1938, when the Navy demanded the impossible, a fighter fast enough to dominate the skies yet tough enough to slam onto a pitching carrier deck, the engineers at Vought realized something terrifying. They were going to have to break the rules to make it happen. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The United States Navy's 1938 specification for a new carrier fighter read like a wish list, written by someone who didn't understand physics. They wanted speed, not just a little more speed than the stubby Grumman F-4F Wildcat that was then entering service, but a quantum leap. 400 miles per hour. They wanted range, enough to escort bombers or patrol vast stretches of the Pacific. They wanted heavy armament, multiple 50-caliber machine guns that could shred enemy aircraft, and they wanted all of this packaged in an airframe strong enough to survive carrier operations, with landing gear robust enough to absorb the bone-jarring impacts of trapped landings on a heaving steel deck. To most aircraft manufacturers, this specification seemed like a polite invitation to fail. But to Rex Beisel, Chance Vaught's chief engineer, it was a challenge he couldn't resist. Beisel was not a man given to half measures. Those who worked with him remembered his single-minded focus, his absolute conviction that speed, above all else, was king. He told his 90-man engineering staff repeatedly, there would be no compromises on that point. If the Navy wanted the fastest carrier fighter ever built, they would get it, even if it meant throwing out every conventional wisdom about naval aircraft design. The problem was power. Or more precisely, the problem was harnessing power. Pratt & Whitney had just developed their R2800 Double Wasp, an 18-cylinder twin-row radial engine that produced 1,850 horsepower for takeoff, with potential to reach 2,000. This was roughly double the power of engines in current Navy fighters. It was a monster. But raw power meant nothing if you couldn't translate it in thrust, and that required a propeller, a very large propeller. The aerodynamicists on Beisel's team, including a young engineer named Alfred Sibila, ran the calculations. Using Hamilton Standard's new propeller design handbook, they determined the aircraft would need a 13-foot, 3-inch diameter propeller to efficiently convert the Double Wasp's power into forward motion. For context, that was bigger than the propeller on many twin-engine bombers of the era. It was enormous, and it created an immediate, seemingly insurmountable problem. The propeller had to clear the ground during takeoff and landing. That was not negotiable. Physics and concrete don't compromise. To provide adequate clearance for a 13-foot propeller on a low-wing monoplane, the conventional solution would be landing gear struts extending perhaps 6 or 7 feet from the wing to the ground. But carrier operations demanded short, stout landing gear. Long, spindly struts would crumple like toothpicks under the violent deceleration of a carrier trap. The forces involved in arrested landings were brutal. A fighter hitting the deck at 70 miles per hour and stopping within 200 feet experienced deceleration that could reach 4 or 5 Gs. Landing gear had to be brutally strong, which meant short and thick, not tall and fragile. The design team found themselves trapped between two absolute requirements that couldn't coexist. They needed ground clearance for the propeller, which demanded long landing gear. They needed carrier capability, which demanded short landing gear. Something had to give. And this is where the story becomes interesting, because the solution they found wasn't in any textbook, it wasn't in any NACA technical report. It came from a moment of frustration in a crowded office. Early in 1938, Beisel called a meeting. Present were James Shoemaker, the assistant chief engineer; Paul Baker, chief of aerodynamics and flight test; William Schoolfield, head of aerodynamics; Ernest Mailloux, chief of structures; George Darracott, head of weights; Fred Dickerman from design; and Alfred Sibilla, representing aerodynamics. They gathered in Beisel's office to review the preliminary design studies, and the mood was grim. Every configuration they examined had fundamental flaws. A high-wing design would work, raising the engine high enough for propeller clearance with short landing gear. But high wings created terrible visibility problems for carrier approaches, and aerodynamic interference between the wing and fuselage would cost precious speed. Mid-wing designs solved some problems, but required landing gear that retracted into the fuselage, eating up space needed for fuel tanks and creating structural nightmares. Low-wing designs offered the best aerodynamics and visibility, but brought them right back to the landing gear length problem. They were sketching configurations on desk pads, crossing them out, trying again. And then, according to Sibila's recollection years later in a February 1995 article for Proceedings magazine, Beisel looked at a low-wing sketch and asked a question that seemed almost naive in its simplicity. He said, and these are close to his exact words, "Why don't we just leave the wing low, put a little bend in it at the landing gear station, and let it rise to meet the fuselage at right angles?" There was a moment of silence. The other engineers looked at each other. An inverted gull wing. It was not a new concept. The Junkers Ju-87 Stuka dive bomber used one. But on a carrier fighter designed for maximum speed, the bent wing would be heavier than a straight wing, more complex to manufacture. The structural engineering would be challenging. Was it worth it? Sibila and the aerodynamicists ran quick calculations right there in the meeting. The angled section where the wing met the fuselage would actually reduce drag compared to using wing root fairings, those bulbous blending pieces needed when wings met fuselages at awkward angles. And if they kept the wing perpendicular to the fuselage at the connection point, they would achieve nearly the same low drag as a perfect mid-wing configuration. The numbers worked. It would be heavy, yes, difficult to build, certainly, but it would solve their impossible problem. Beisel made the decision that afternoon. The inverted gull wing would be the basic element of the XF4U-1 design. The bent wing bird, as it would later be nicknamed, had just been born. But approval from a chief engineer in a private meeting was one thing. Proving the concept would actually work in the real world was something else entirely. Because the truth is, radical design decisions make corporate executives nervous. And in 1938, with war clouds gathering over Europe but America still at peace, Vought couldn't afford to bet its future on an unproven concept without some form of validation. They needed data. They needed wind tunnel results. They needed proof from NACA, the National Advisory Committee for Aeronautics, the government agency responsible for aeronautical research. And here's where the story takes its controversial turn, because getting that proof might have required some creative interpretation of proper procedures. Wind tunnels in the late 1930s were precious, tightly scheduled resources. NACA's Langley facility in Virginia had several tunnels of different sizes and capabilities, from the small variable density tunnel to the massive full-scale tunnel that could test actual aircraft. But time in these tunnels was allocated through official channels. Manufacturers submitted formal requests. Government engineers reviewed priorities. Schedules were made months in advance, and for a radical, unproven design like the Corsair's inverted gull wing, getting priority tunnel time before the Navy had even awarded a contract would have been difficult. Perhaps impossible. The engineering team needed to validate their wing configuration quickly. They needed to confirm that the bent wing wouldn't create unexpected drag penalties or airflow problems. They needed hard data, not just calculations on paper. And so, according to some accounts, though records here are frustratingly vague, someone at Vought may have found a way to get that data through unofficial channels. The details have been lost to time, buried in filing cabinets or destroyed when Vought moved its operations from Connecticut to Texas. But the whispers persisted for years among old-timers in the aviation industry that maybe, just maybe, wind tunnel tests for the Corsair's wing happened off the books. Bootleg testing, done during odd hours or squeezed into time allocated for other projects. Results obtained through personal friendships with NACA engineers rather than official paperwork. Was it illegal? That's too strong a word. Government contracting in 1938 wasn't the bureaucratic maze it would later become. Relationships between NACA engineers and aircraft companies were informal, collaborative. The line between official testing and friendly consultation was blurry. But was it unauthorized? Possibly. Did it bend the rules? Perhaps. The truth is, we'll likely never know for certain. What we do know is this. By June 1938, when the Navy awarded Vought a contract to build a prototype bearing the factory designation V166B, the design was remarkably mature for such a short development period. The inverted gull wing wasn't a gamble anymore. It was a calculated engineering solution, backed by data that somehow, someone had managed to acquire. The contract called for the construction of one experimental prototype, the XF4U-1, Bureau number 1443. Rex Beisel and his team now had to turn their bent wing concept into actual metal and prove it could fly. They had 18 months. The mock-up inspection came in February 1939, where Navy representatives examined a full-scale wooden model of the aircraft to check that everything met specifications. Then construction began in earnest. The Chance Vought plant was simultaneously being moved from East Hartford to Stratford, Connecticut, adding chaos to an already compressed schedule. Engineers and manufacturing experts worked side by side, solving problems in real time. The inverted gull wing created structural puzzles no one had faced before on a fighter aircraft. They had to figure out how to integrate slotted flaps into the curved gull wing section. They had to design a landing gear retraction system that could fold the gear up and back, then rotate it 90 degrees, so the wheels lay flat inside the wing's thickness. They borrowed this rotating gear concept from their own SB2 U-1 Vindicator, proving that sometimes the best innovations come from cannibalizing your own previous work. They had to build special jigs, enormous fixtures that held the wing center section and lower fuselage so they could be constructed as a single unit. This was critical for structural integrity. The stresses of carrier landings would try to tear that wing fuselage joint apart. It had to be incredibly strong. The result was an immensely robust structure, probably over-engineered by modern standards, but absolutely necessary given the forces involved. And all the while, in the back of everyone's mind was the knowledge that this airplane had to be fast. Speed was king. Beisel wouldn't accept compromises. So every decision, every component, was examined through that lens. Could they make it cleaner? Could they reduce drag? The landing gear doors were designed to completely enclose the wheel wells when the gear retracted, leaving a streamlined wing surface. The oil coolers were tucked into the wing roots alongside the supercharger air intakes, using openings in the leading edges rather than protruding scoops that would add drag. Nothing was allowed to disturb the airflow unless absolutely necessary. By May 1940, the prototype was complete. It sat in the hangar, dark blue paint gleaming, that distinctive bent wing profile unmistakable. The XF4U-1 was big for a single-seat fighter. When Lyman Bullard stood next to it, the top of the engine cowling came up to his chest. They had built a set of handholds and footsteps into the right side of the fuselage beneath the cockpit, so pilots could climb in without a ladder. The message was clear. This was not a delicate machine, this was a brute, built to dominate. On May 29, 1940, Bullard fired up the prototype for its maiden flight. The R2800 engine, serial number XR2800-4, produced 1,805 horsepower. That massive propeller bit into the air, and the XF-4U lifted off from Stratford. The flight was intended to be brief, just a few circuits to check basic handling. It proceeded normally until, without warning, the elevator trim tabs began to flutter violently. Bullard immediately cut the flight short and made a hurried landing. The engineering team discovered the trim tabs were failing due to flutter, oscillating so rapidly in the airstream that they were in danger of breaking off. It was the first of many problems they would have to solve, but they fixed it, reinforced the trim tabs, adjusted the control linkages. And 2 months later, on October 1st, 1940, Bullard took the XF-4U up again. This time, he was under orders to push it, see what it could really do. He climbed to altitude, leveled off, and opened the throttle. The engine roared to full power, the propeller became a blur, and the airspeed indicator needle crept upward. 300 miles per hour, 350, 380. It kept climbing. Bullard held the throttle forward, watching the needle. 400, 404 miles per hour. In level flight. No dive, no tricks, just raw, honest speed. When he landed and reported the results, there was initially skepticism. Was the airspeed indicator calibrated correctly? Was there a tailwind? But after verification flights and careful analysis, the number held. The XF-4U-1 had just become the first American single-engine fighter to exceed 400 miles per hour in level flight. At a time when the Grumman F-4F Wildcat topped out around 320, this was revolutionary. This was the future. The Navy took notice. Formal acceptance trials began in February 1941. There were issues, of course. The airplane had nasty spin recovery characteristics. The inverted gull wing interfered with elevator authority in certain flight regimes, making spins difficult to recover from. Test pilot Boone Guyton, who would later become Vaught's chief experimental test pilot, was asked years afterward by Navy pilots about spinning the F-4U. His answer was succinct: don't. There were also armament concerns. The prototype had been designed with two .30 caliber machine guns in the nose, synchronized to fire through the propeller, and one .50 caliber gun in each wing. But reports from the air war raging in Europe made clear this armament was inadequate. German fighters were carrying 4 or more heavy machine guns or cannons. The Japanese Zero had two 20mm cannons and 2 machine guns. The F-4U would be outgunned. In November 1940, when the Navy requested production proposals, they specified heavier armament. The solution was to eliminate the nose guns entirely and install 350 caliber Browning M2 machine guns in each wing, 6 guns total, all outside the propeller arc. This eliminated the need for synchronization gear and dramatically increased firepower. Each gun would carry 400 rounds, giving the pilot roughly 40 seconds of ammunition at 600 rounds per minute cyclic rate. That was far more trigger time than any opponent, but adding 6 heavy machine guns with 2,400 rounds of ammunition added weight, a lot of weight, several hundred pounds. And weight is the enemy of speed. The engineers had to make hard choices. They compensated by using lightweight materials wherever possible. The ailerons, the control surfaces on the wings that made the aircraft roll, were constructed with wooden frames and plywood skinning to save weight. Later production models would use aluminum, but in 1941 they needed every trick they could find. On March 3, 1941, the Navy entered into a letter of intent to buy the aircraft. On April 2nd, Vought submitted their production proposal. On June 30th, 1941, the Navy awarded contract number 1443 for 584 F-4U-1 fighters. The aircraft was given the name Corsair, inherited from Vaught's late 1920s O-2U naval biplane Scout, which had first borne that name. It was official. They were going into production. But between placing an order and getting a fully combat-ready aircraft into the hands of fleet squadrons lay a brutal 18-month gauntlet of testing, modification, failure, and redesign. Because as brilliant as the inverted gull wing solution was, it had introduced problems nobody anticipated. Problems that would nearly kill the entire program before a single Corsair ever saw combat. The first production F4U-1 was delivered to the Navy on July 31, 1942. By this point, America had been at war for nearly 8 months. Pearl Harbor had galvanized the nation. Naval aviation was desperately short of modern fighters. The Wildcat was struggling against Japanese Zeros in the brutal air combat over Guadalcanal and the Solomon Islands. The Corsair was supposed to be the answer, the aircraft that would give American pilots overwhelming superiority. But first, it had to prove it could actually operate from aircraft carriers. And that's where everything went wrong. Carrier qualification trials began on the training carrier USS Wolverine and escort carriers USS Core and USS Charger in autumn 1942. The results were terrifying. Pilots quickly discovered the Corsair was a handful, even in perfect conditions, and carrier landings are never perfect conditions. The problems started with visibility. The framed birdcage canopy, with its metal struts and small glass panels, gave poor visibility for deck taxiing. On a carrier, where deck crew are running around and aircraft are parked with mere feet of clearance, you need to see where you're going. The Corsair made that nearly impossible, but the real killer was that long nose. The nose section stretched 14 feet in front of the pilot. When the Corsair sat in takeoff position, tail down and nose pointed up at the angle required by the tall landing gear. The nose blocked forward vision to about 12 degrees above the horizon. This made it virtually impossible to see the landing signals officer during final approach to the carrier. The LSO, standing on a platform at the rear of the carrier deck, used colored paddles to guide pilots to a safe landing. Pilots had to keep the LSO in sight, but once a Corsair was aligned with the deck on final approach, the pilot couldn't see the LSO anymore. The long nose blocked him completely. Adding insult to injury, the R-2800 engine had issues with oil and hydraulic fluid leaking from the engine compartment. These leaks weren't dangerous to the aircraft, but they were catastrophic for visibility. Fluid seeped past the cowl flaps and smeared across the windshield. Pilots trying to make precision carrier approaches found themselves looking through a film of oil, unable to see clearly. In good weather, this was merely dangerous. In poor weather, or at night, it was suicidal. Then there were the handling characteristics at slow speed. Carrier landings require the pilot to slow the aircraft to just above stall speed as they cross the carrier's fantail. The goal is to touch down, catch an arresting wire with the tailhook, and stop within a couple hundred feet, but the F4U had vicious stall characteristics. The left wing could stall suddenly and drop without warning. If this happened during landing, the aircraft would flip over before the pilot could react. Even worse, if a pilot was waved off, meaning told to abort the landing and go around for another try, they had to rapidly advance the throttle to full power. But the enormous torque from the R-2800 engine, especially the sudden surge when throttle was quickly advanced, could cause the Corsair to flip over on its back. Several pilots died learning this lesson, and if you somehow managed to avoid stalling, avoid flipping over from engine torque, and actually got the aircraft lined up for touchdown, there was one final demon waiting. The Corsair bounced. The landing gear oleo struts, the shock absorbers that cushion the impact of landing, were too stiff. When the Corsair touched down on a carrier deck, instead of absorbing the impact smoothly, the gear would compress and then spring back like a pogo stick. The aircraft would bounce back into the air, sometimes 10 or 15 feet. Now the tailhook, which should have caught an arresting wire, was uselessly high off the deck. The aircraft would slam back down uncontrolled, possibly missing all the arresting wires and crashing into the barricade. Or in the worst case, tumbling off the forward end of the deck into the ocean. Navy pilots who tested the Corsair in carrier qualifications gave it brutal nicknames: the Hog, the Hose Nose, the Bent Wing Widowmaker. They didn't say these names with affection. They said them with frustration and fear. Some pilots refused to fly it. There was talk of cancelling the entire program, of writing off the Corsair as a failed experiment and focusing resources on Grumman's F-6F Hellcat, which used the same R2800 engine but had far gentler handling characteristics. But there was a problem with simply cancelling the Corsair. Despite all its faults, despite the terror it induced in carrier approaches, it was still the fastest, most powerful fighter the Navy had. Once airborne and in combat, it was magnificent. The speed, the firepower, the ruggedness of that big radial engine, all of it combined to create an aerial predator without equal. Pilots who flew it in training, away from the stress of carrier operations, reported it was a dream, fast, responsive, forgiving, at high speed. The Corsair wasn't a bad design, it was just a bad carrier aircraft. And that distinction gave the Navy an idea. In late 1942, as the situation in the South Pacific grew increasingly desperate, Marine Corps squadrons on Guadalcanal were flying old F-4F Wildcats, and even some obsolete fighters scrounged from any source they could find. They were outnumbered, outgunned, and losing pilots at an unsustainable rate. The Japanese held air superiority, and American forces on the ground were taking heavy casualties from constant air attacks. The Marines needed better fighters, immediately, and they didn't need carrier-capable fighters. They were operating from land bases. Rough dirt strips carved out of jungle, yes, but still land. No carrier traps, no landing signal officers, no deck pitching in swells. The decision was made. The Corsair would be given to the Marines for land-based operations. The Navy would focus on the Hellcat for carrier duty. It wasn't the originally intended use for the aircraft, and some at Vought saw it as an admission of failure. But to the Marines who would receive these fighters, it was a lifeline. And in February 1943, Marine Fighting Squadron 214, VMF 214, flew the first combat mission with Corsairs from Henderson Field on Guadalcanal. They were led by Major Gregory Pappy Boyington, who would become one of the most famous aces of the Pacific War, credited with 22 kills in F4US. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Marines immediately loved the Corsair. On land, where visibility during approach wasn't critical, and where you could see the runway from pattern altitude, the long nose was merely an annoyance. The stiff landing gear, still a problem, but dirt and coral runways had more give than steel carrier decks. The aircraft still bounced, but not as violently. And the engine torque issue? Experienced pilots learned to anticipate it, to feed in right rudder when advancing the throttle to compensate for the left-turning tendency. It became second nature. What mattered to the Marines was what happened once the wheels left the ground. And there, the Corsair was everything they had been promised. It was fast enough to run down any Japanese fighter. The Zero could outturn it at slow speed, but the Corsair could dive away from any situation, build speed, and then use that speed to climb back to altitude or reverse for another attack. American pilots learned boom and zoom tactics. Dive on the enemy from above, make a high-speed firing pass, then use your superior speed to climb back to altitude before the enemy can react. The Zero couldn't follow. Its light airframe and low wing loading, which gave it superb maneuverability at low speeds, became a liability at high speeds. The Corsair, built like a brick with wings, stable and heavy, excelled in high-speed combat. The 650 caliber Browning M2s, 3 in each wing, were devastating. Each gun fired armor-piercing incendiary rounds at 600 rounds per minute. When all 6 guns converged on a target, they delivered nearly 60 pounds of lead per second. Japanese aircraft, constructed lightly to save weight and lacking armor protection, or self-sealing fuel tanks, disintegrated under this firepower. A 1-second burst was often enough. 2 seconds was overkill. Corsair pilots reported enemy fighters literally exploding, wings tearing off, fuselages breaking apart in mid-air. And the R2800 Double Wasp proved incredibly resilient in combat. Japanese pilots would make desperate head-on attacks, their 7.7mm and 20mm weapons hammering away at the big radial engine. Bullets would punch holes in cylinders, sever fuel lines, damage the supercharger. But the engine kept running. The 18 cylinders gave it redundancy. Lose 1 or 2 cylinders, and you still had enough power to get home. The large displacement meant even damaged, it produced usable horsepower. Marines brought Corsairs back to base with engines so shot up they leaked oil and ran rough, but they ran. That counted for everything. The Japanese quickly learned to fear the Corsair. They called it whistling death, because of the distinctive sound it made in a dive. The wind rushing through the engine, cooling vents and supercharger intakes created a high-pitched whistle that could be heard on the ground long before the aircraft appeared. To Japanese troops, that whistle meant incoming death. Bombs, rockets, or strafing runs were seconds away. There was no defense, just the shrieking whistle, growing louder, and then the hammer blow of high explosives or 50 caliber rounds chewing through positions. By mid-1943, Corsair squadrons were racking up impressive kill ratios. VMF 214, Boyington's Black Sheep, shot down 97 Japanese aircraft and damaged another 103 during their 2 6-week tours of duty. VMF 124, commanded by Major William Giese, produced multiple aces. VMF 215, known as the Fighting Corsairs, became one of the highest-scoring squadrons in the Pacific. The numbers told the story. In the hands of skilled pilots, the Corsair was achieving kill-to-loss ratios that approached 11-1. For every Corsair lost in air combat, 11 Japanese aircraft were destroyed. This wasn't just about the aircraft. American pilot training was superior. Tactics were more sophisticated. Intelligence from broken Japanese codes gave warnings of incoming attacks. But the Corsair's raw performance made these advantages decisive. Japanese pilots simply couldn't match its speed or firepower. Even the vaunted Zero, which had terrified Allied pilots earlier in the war, was now outclassed. The Corsair could choose when to fight and when to disengage. Control of engagement timing is control of the battlefield. Back home at Vought, engineers were working on refinements. The F4U-1A introduced a raised pilot seat and a bulged cockpit canopy, improving visibility. The long nose was still there, but at least pilots could see better to the sides and rear. The F4U-1C, which appeared in 1943, replaced the 650 caliber guns with 420mm cannons. This variant was less popular. The cannons had more punch per shell, but lower rate of fire and less ammunition. Most pilots preferred the sustained firepower of the 650s. The F4U-1D, which entered service in April 1944, brought significant improvements. The R2800 engine was upgraded to the -8W variant, equipped with water injection. This system injected a mixture of water and methanol into the engine during takeoff or combat, cooling the intake charge and allowing higher manifold pressure. The result was a temporary boost to 2,250 horsepower, war emergency power, they called it. Good for about 5 minutes before you had to throttle back or risk damaging the engine. But 5 minutes at that power level could mean the difference between escape and death. The -1D also featured permanent launching rails for rockets and twin pylons for bombs or drop tanks. The Corsair was evolving from pure fighter to fighter-bomber, capable of carrying significant ordnance. Marines discovered it could haul 2,000-pound bombs or up to 8 5-inch high-velocity aircraft rockets. This transformed close air support. When troops on the ground called for airstrikes, Corsairs would come in low, maybe 50 feet off the deck, and unleash rockets or bombs with devastating accuracy. The Japanese had no answer. Their anti-aircraft fire was ineffective against aircraft moving that fast at that altitude. But the most significant improvement in the -1D was subtle. A single-piece blown clear-view canopy replaced the framed birdcage. This new canopy was a seamless bubble of plexiglass, providing 360-degree visibility. Pilots could finally see around them properly, could check 6 o'clock without fighting with frame posts obstructing their view. It seems like a small thing, but in air combat, seeing the enemy first is often the difference between victor and victim. Production ramped up dramatically through 1943 and 44. Vought's Stratford plant couldn't build Corsairs fast enough to meet demand, so additional contracts went to Goodyear, whose Corsairs were designated FG, and Brewster Aeronautical Corporation, designated F3A. Goodyear did excellent work. Brewster, plagued by internal management problems and corruption, struggled. The Navy eventually cancelled Brewster's contract in 1944 after they managed to produce only 735 aircraft in over a year, most of which required extensive rework before they were combat-ready. Still, Corsairs were rolling off assembly lines by the thousands. By the end of 1944, the type was in service not just with the Marines but also with Navy squadrons, both land-based and increasingly on carriers. Because quietly, away from public view, Vought engineers and Navy test pilots had finally solved the carrier suitability problems. It hadn't been one fix. It had been dozens of small improvements, incrementally making the aircraft safer for carrier operations. They modified the main landing gear oleos, softening them so the bouncing was reduced. They installed a taller tailwheel assembly, changing the aircraft's angle when sitting on the ground. This raised the nose slightly, improving forward visibility during taxi. They added that stall strip to the leading edge of the outer right wing, a small 6-inch-long strip of metal that disrupted airflow just enough to prevent the sudden, asymmetric wing stall that had killed pilots. These modifications, combined with improved pilot training and new approach procedures, finally made carrier operations feasible. The British Fleet Air Arm, which had been operating Corsairs on Royal Navy carriers since 1943, had actually solved the visibility problem before the Americans. British pilots developed a curved approach technique. Instead of the traditional straight-in final approach, they would turn downwind, then make a slow, continuous curving turn that brought them into alignment with the deck only at the last moment. This kept the landing signals officer in sight throughout the approach. American pilots initially resisted this technique, seeing it as unorthodox and potentially dangerous. But after British pilots demonstrated its effectiveness, the curved approach became standard procedure for Corsair carrier landings. By early 1944, Navy fighter squadrons were beginning to transition to Corsairs for carrier duty. VF-17, the Jolly Rogers, commanded by Lieutenant Commander Tommy Blackburn, became one of the most famous Navy Corsair squadrons. Flying from land bases in the Solomon Islands, they shot down 152 Japanese aircraft and produced 11 aces. When VF-17 eventually transitioned to carrier operations, they proved the Corsair could hold its own alongside Hellcats on the crowded flight decks. The F4U-4, which appeared in 1945, represented the ultimate evolution of the Corsair design during World War II. This variant featured the R2800-18W engine, a significantly upgraded power plant. The new engine incorporated a 2-stage supercharger with automatic controls, giving it excellent performance at high altitude. With water injection engaged, it produced 2,450 horsepower. The air intake for the supercharger was relocated to a chin scoop under the engine cowling, giving the -4 a distinctive profile compared to earlier models. The cockpit was completely redesigned with modern instruments and better layout. The cowling was lowered 2 degrees to improve forward visibility. Spring tabs were added to the elevators and rudder to reduce control forces at high speed. The tail wheel became fully retractable. Every detail was refined, polished, perfected, and the result was extraordinary. The F4U-4 was clocked at a top speed of 446 miles per hour at 26,200 feet altitude. The earliest Allied jets, the British Meteor and German Me-262, were only marginally faster, and only at low altitude where jet engines had their best performance. At 446 miles per hour, the Corsair was faster than almost every propeller-driven fighter in the world, faster than the P-51 Mustang at most altitudes, faster than the German FW-190D, comparable to the P-47 Thunderbolt at altitude, and critically, it achieved this speed not with exotic engineering or temperamental systems, but with refinements to a fundamentally sound design. The inverted gull wing, that solution sketched on a desk pad in a crowded office back in 1938, had proven itself beyond any doubt. Production of the -4 began in October 1944, but most didn't reach combat units until early 1945. By that point, the war in the Pacific was entering its final, bloodiest phase. The battles for Iwo Jima and Okinawa saw Corsairs flying close air support missions in some of the most intense combat of the war. Marines on the ground called them the Sweetheart of Okinawa, a nickname that captured the profound gratitude infantry felt when they saw those bent-wing fighters screaming overhead, delivering napalm, rockets, and bombs on Japanese positions. Okinawa also marked the height of the kamikaze threat. Japanese pilots, desperate to stop the American advance, began flying suicide missions against the invasion fleet. Hundreds of aircraft, many flown by barely trained pilots with just enough skill to take off and point their planes at targets, were thrown at American ships in waves. The kamikaze attacks were terrifying in their intensity. Pilots who survived multiple missions described the psychological horror of watching planes deliberately fly into ships, knowing the pilot was choosing death. Corsairs became critical to the anti-kamikaze defense. Their speed allowed them to intercept incoming raids at maximum range from the fleet. Their firepower could destroy attackers before they reached terminal dive. Navy and Marine Corsair squadrons flew combat air patrols constantly, vectored by shipboard radar controllers toward incoming threats. The kill tallies from Okinawa are staggering. Corsair pilots claimed hundreds of Japanese aircraft destroyed, many of them kamikazes shot down before they could reach their targets. But not all Corsair combat was in the Pacific. A lesser-known chapter of Corsair history played out in the European theatre. The British Fleet Air Arm operated Corsairs from carriers in operations against German targets in Norway and during the final assault on Japan. Their Corsairs had clipped wingtips, reduced by about 8 inches on each side, to allow them to fit in the lower hangars of Royal Navy carriers. This modification slightly reduced range and roll rate, but made no appreciable difference in combat effectiveness. British Corsair pilots participated in strikes against the German battleship Tirpitz and in suppression missions against coastal defences. They found the aircraft just as capable in European skies as it had been in the Pacific. The only significant difference was the cold. Operating from carriers in the North Atlantic or Norwegian Sea meant dealing with temperatures far below anything encountered in tropical Pacific operations. The R-2800 engine, designed for warm weather, sometimes had starting difficulties in extreme cold. But British ground crews developed workarounds, and the missions continued. By August 1945, when Japan surrendered, Corsairs had been credited with shooting down 2,140 Japanese aircraft in air-to-air combat. Against those victories, only 189 Corsairs had been lost to enemy fighters. The 11-to-1 kill ratio held across thousands of combat missions, across 2 years of brutal warfare, across every theatre where Corsairs flew. It was one of the most successful combat records of any fighter aircraft in history. But raw numbers don't capture the full story. They don't convey what it felt like to be a young pilot, 21 or 22 years old, strapping into that big fighter for the first time. The cockpit sat well back on the fuselage, behind the enormous engine. Climbing in, you had to use those handholds on the side, pull yourself up onto the wing, step over into the cockpit. The seat was armoured, steel plate behind you to stop bullets. The instrument panel was crowded with gauges. Engine instruments, flight instruments, fuel gauges, ammunition counters, everything you needed within reach. You'd run through the startup checklist: fuel selector on main tank, mixture rich, props full, forward. Throttle cracked about an inch. Master battery on, boost pump on to pressurize the fuel system. Then hit the starter. The big Pratt & Whitney would cough, cylinders firing randomly, belching smoke from the exhaust stacks. Then it would catch, smooth out, settle into that distinctive radial rumble. 18 cylinders firing in sequence, a deep rhythmic thunder that you felt in your chest. Taxiing was an adventure. You couldn't see forward at all. You had to S-turn, weaving left and right, trying to catch glimpses of the taxiway ahead through the side windows. On a crowded carrier deck or busy airfield, this required intense concentration. One moment of inattention and you'd clip a wing on another aircraft or run over a deck crew member. The tail wheel was steerable, but the long nose and narrow track made the Corsair want to ground loop, to pivot around one main gear if you weren't careful with rudder and brake. Takeoff was straightforward. Line up on the runway, advance throttle smoothly. The engine roared. 2,000 horsepower pushing 13 tons of fighter down the runway. Keep right rudder in to counter torque. Watch the airspeed indicator. 60 knots, 70. At 80 knots, ease back on the stick. The nose lifted. Suddenly you could see forward as the tail came up. Another few seconds and the rumble of tires on pavement stopped. You were airborne. Gear up. Watch the wheels rotate 90 degrees and retract into the wing. Flaps up. Climb speed 160 knots. The Corsair would climb at 3,000 feet per minute, when light, 2,000 feet per minute, loaded for combat. Once at altitude, trimmed for level flight, the Corsair was stable and easy to fly. The controls were well harmonized. Ailerons a bit heavy at low speed, but light and responsive at high speed. Rudder effective. Elevator powerful but not twitchy. You could fly formation for hours without fatigue. You could make gentle turns, steep turns, rolls, whatever you needed. The aircraft was predictable, honest. But where the Corsair truly came alive was in combat maneuvering at high speed. Most fighters of that era had controls that became heavy and sluggish above 300 miles per hour. Not the Corsair. Above 350, 400 miles per hour, the controls stayed responsive. You could pull hard turns, snap rolls, high-speed reversals. The airframe was stressed for something like 11 Gs, far beyond what a human pilot could endure. The Corsair's limits were defined by the pilot's physiology, not the aircraft's structure, and that gave enormous confidence. You could throw the aircraft around violently, knowing it wouldn't break. The 650 caliber Brownings were bore-sighted to converge at 300 yards. At that range, all 6 streams of fire crossed at a single point, creating a cone of destruction about 6 feet in diameter. Put that cone on an enemy aircraft and hold the trigger. The whole plane would shudder from recoil. Tracers would arc out, every 5th round glowing bright orange. You'd see impacts walking across the target, pieces flying off, smoke, flash of fire, and then the enemy would roll over and fall, trailing flame. Experienced pilots learned to fire in short bursts, 1 or 2 seconds. Check your aim. Fire again. This conserved ammunition and gave you time to adjust if you were missing. But in the heat of combat, with an enemy in your sights and adrenaline flooding your system, discipline was hard. Pilots would hold the trigger down, burning through all 400 rounds per gun in 40 seconds, then find themselves defenseless with half the mission still ahead. It happened, more often than anyone wanted to admit. Returning to base after a mission, low on fuel and ammunition, possibly damaged, you'd set up for landing, extend landing gear. 3 green lights confirming gear down and locked, lower flaps, slow to approach speed, about 90 knots, line up on the runway or on the carrier deck, if you were Navy. The nose would be up slightly, blocking forward view again. You'd be looking out the side, judging height and distance by peripheral vision and instinct. Over the threshold, throttle back, let it settle. The stiff landing gear would hit hard, even on a smooth runway. On a carrier, you'd feel the jolt of the tail hook catching the wire, 7 tons of fighter decelerating from 70 knots to 0 in less than 2 seconds. Your body would slam forward against the shoulder straps. Everything loose in the cockpit would fly forward. Then, silence. Engine idling. Wind noise. Gone. Just the creak of the airframe settling and the deck crew running toward you with chocks for the wheels. That was a Corsair mission. Repeated hundreds of times by thousands of pilots over 2 years of war. Each time, the knowledge that maybe this time you wouldn't come back. Maybe today a 0 would get on your 6 and you wouldn't see it in time. Maybe flak would hit the engine or sever a control cable. Maybe you'd run out of fuel on the way back and have to ditch in the ocean, hoping a submarine or destroyer would find you before sharks or exposure killed you. The Corsair gave you the best possible chance, but it couldn't guarantee survival. Nothing could. After the war ended, Many thought the Corsair's story was over. Jet fighters were the future. The Navy was already testing the McDonnell F-H Phantom, the first American carrier-capable jet fighter. The Air Force had the Lockheed P-80 Shooting Star. Propeller-driven fighters seemed obsolete, relics of a war that was finished. But the Corsair refused to become obsolete, because while jets were fast at high altitude, they were fuel inefficient and had limited range. For ground attack missions, for close air support where you needed to loiter over the battlefield for extended periods, jets couldn't match piston-engine aircraft, so the Corsair stayed in production. The F-4U-5 appeared in 1946 with an even more powerful R2800-32 engine and refined aerodynamics. Maximum speed increased to 470 miles per hour. The -5 was the first all-metal Corsair, with aluminum outer wing panels replacing the fabric-covered ones of earlier models. Spring tabs on all control surfaces reduced pilot workload. An improved cockpit with better instruments and layout made long missions less fatiguing. Then came the AU-1, a specialized attack variant designed specifically for the Marines. The AU-1 sacrificed high-altitude performance for low-level capability. The supercharger was simplified since the aircraft would operate below 10,000 feet. Extra armor was added to protect the pilot and fuel tanks from ground fire. The oil coolers were relocated inboard, away from the wing routes where they were vulnerable to small arms fire, and the payload capacity was increased dramatically. The AU-1 could carry 8,200 pounds of bombs, rockets, or napalm. That was more than many twin-engine light bombers. The AU-1 was slow. Maximum speed when loaded for combat was only 238 miles per hour. But for close air support, speed mattered less than payload and survivability. And the AU-1 could absorb tremendous battle damage and keep flying. Marines loved it. They called it the tank, and the nickname was affectionate. Goodyear developed the F-2G Super Corsair, installing the massive Pratt & Whitney R4360 Wasp major engine. This 28-cylinder, 4-row radial produced 3,600 horsepower. It was absurd. The F-2G could exceed 450 miles per hour at sea level. But the R4360 was maintenance-intensive and temperamental. Only a handful of F-2Gs were built before the program was cancelled. 2 survive today in airworthy condition, prized by warbird collectors for their raw, brutal power. When the Korean War began in June 1950, the Corsair was thrust back into combat. Navy and Marine squadrons flying F-4U-4s and -5s deployed to Korean waters aboard carriers. The AU-1 was rushed into production, with deliveries beginning in 1952. These aircraft would see heavy combat over the next 3 years, proving once again that written-off technology could still be devastatingly effective in the right role. Korea was a different war from the Pacific. The enemy had jet fighters, MiG-15s, supplied by the Soviet Union. These swept-wing jets could fly at 650 miles per hour and climb to 50,000 feet. A Corsair had no chance in air-to-air combat against a MiG-15, but that wasn't the mission. The mission was close air support, and there, the Corsair excelled just as it had in World War II. Marine and Navy Corsair pilots flew thousands of sorties supporting United Nations ground forces. They attacked North Korean and Chinese troop concentrations, supply depots, bridges, railroads, anything that supported enemy operations. They flew in all weather, in brutal cold that made starting the big radial engines an ordeal. They flew through heavy anti-aircraft fire from North Korean gunners equipped with Soviet weapons, and they kept flying, kept attacking, kept supporting the infantry on the ground. The Corsair's ability to carry heavy loads and loiter over the battlefield made it invaluable. A jet fighter might scream in, drop its bombs in one pass, and be gone. A Corsair could circle the battlefield, waiting for ground controllers to identify targets, then make repeated attacks until its ammunition was exhausted. Forward air controllers, usually Marine officers on the ground with infantry units, developed deep trust in Corsair pilots. They knew if they called for air support, the Corsairs would show up and stay until the job was done. One of the most remarkable missions of the Korean War involved a Corsair pilot named Lieutenant Robert Klingman of VMF 312. On May 10, 1951, Klingman was escorting a reconnaissance aircraft at high altitude when they encountered a Japanese-built, propeller-driven reconnaissance plane, probably a modified Ki-46. At 33,000 feet, far above the Corsair's optimal altitude, Klingman's guns froze. The lubricant in the gun mechanisms had thickened in the extreme cold, jamming the weapons solid, but Klingman was not about to let the enemy aircraft escape. He maneuvered his Corsair until he was directly behind the reconnaissance plane, then carefully, deliberately, flew forward until his propeller chewed into the enemy's tail. The propeller blades, spinning at 2,000 RPM, acted like a buzzsaw. They shredded the enemy's tail section. The reconnaissance plane rolled over and went down. Klingman nursed his badly vibrating Corsair, its propeller bent and damaged, back to base, and somehow managed to land successfully. It was one of the most audacious kills of the war, and it exemplified the aggressive spirit of Corsair pilots. By the time the Korean War armistice was signed in July 1953, Corsairs had flown more than 64,000 combat sorties in Korea. They had destroyed hundreds of bridges, thousands of vehicles, countless enemy positions. Their contribution to the ground war was immense, and they had proven that a well-designed aircraft from World War II could still be relevant and effective a decade later, even in the jet age. The last Corsair rolled off Vought's Dallas production line in December 1952. The final recipient was the French Navy, which operated Corsairs in Indochina and later in Algeria. Total production across all variants and manufacturers reached 12,571 aircraft. It was one of the longest production runs of any fighter aircraft in history, spanning more than 11 years. Looking back, the Corsair's success seems almost inevitable, but it wasn't. It came from hundreds of decisions, large and small, made by engineers and test pilots who refused to accept compromise. It came from a chief engineer who had the audacity to sketch a bent wing on a desk pad and declare it the solution to an impossible problem. It came from test pilots who flew prototypes with known dangerous characteristics, pushing limits to find where the aircraft would break so engineers could fix it. It came from production workers who riveted, welded, and assembled thousands of components into aircraft that had to work perfectly, or men would die. And perhaps, if the rumors are true, it came from someone who knew that sometimes you bend the rules to get the data you need, that sometimes official channels are too slow, too bureaucratic, too cautious for the urgent demands of war, that sometimes you do what's necessary, even if it's not exactly authorized, because lives depend on getting it right. The Corsair's inverted gull wing was brilliant engineering, but brilliant engineering requires data, wind tunnel results, aerodynamic validation, proof that the concept works before you commit millions of dollars and thousands of man-hours to production. How that data was obtained, through what channels, following which procedures, may never be fully known. Files were lost. People who knew the truth took their secrets to their graves. What remains is the aircraft itself and its extraordinary combat record. 446 miles per hour. First U.S. single-engine fighter to exceed 400 miles per hour. 2,140 enemy aircraft destroyed. 11-to-1 kill ratio. 14,900 tons of bombs delivered, 64,000 combat sorties in Korea. These are not the statistics of a failed program or a compromised design. These are the numbers that define dominance. The Corsair was not perfect. No aircraft is. It killed pilots during training. It had vices and quirks that demanded respect and skill. But in the hands of a trained pilot, in combat against enemy fighters or ground targets, it was devastating. And it all traced back to that meeting in 1938, to Rex Beisel asking a simple question about bending a wing, to a team of engineers willing to try something radical. Today, fewer than 30 Corsairs remain in airworthy condition. They're treasured by museums and private collectors, maintained at enormous expense, flown at air shows where crowds gather to hear that radial roar and see the bent wing silhouette. Each flight is a living connection to history, to the men who flew these aircraft in combat, to the engineers who designed them, to the workers who built them. The Corsair is more than metal and rivets. It's a monument to what determined people can achieve when they refuse to accept the impossible. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.